Hey guys, it's been a while since I've chatted with you, but hopefully you read the email. Hopefully you've emailed me back if you have questions. These are the guided notes for the next unit's first lesson. We finished kind of a lesson about confidence intervals and how we can use them to say what we think the population value would be. And we're getting into a lesson about now testing things. So like if some group says that the population proportion is 30%, we can run a test on that. So if you're just following along, fine. If you've got the notes somehow printed off, also fine. But I'm going to fill them out as if I'm standing in front of you in the class. So what we are talking about is called a significance test. So it's just a formal procedure that we're going to go through for using observed data for sample data to decide between two competing claims. These are called hypotheses, which function slightly differently than a scientific hypothesis, but they're called hypotheses. They're claims about the parameter, so the population value that somebody's saying that it is. So for example, a basketball player claims to make 80% of the free throws that he attempts. That is, he claims that his population proportion is 0.8, where P is the true proportion of free throws that he will make in the long run. We expect he's exaggerating, so we think that that value of P is actually less than 0.8. So he says it's 0.8, we think it's less than 0.8. So now we need to actually collect some data. We need to get something from a sample. So suppose the player shoots 50 free throws and makes 32 of them. The sample proportion of shots that are made is the P hat value. So if we put 32 out of 50, we would see that he has 0.64. Now, that is less than 80%. So we do have some evidence to think that he's actually shooting less than 80% of the time, making less than 80% of his shots, but we're trying to figure out if this is convincing evidence that the true proportion value is less than 80%. So is this just sampling variability that we're seeing, or is it plausible? Is it plausible that this could happen by chance alone? Is it just sampling variability? If we had been in class, I would have had us actually conduct this where we would spin a spinner and see how many times it happened for us. We would record it as a class, blah, 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 blah. We clearly didn't do it. So there were two possible options. What could happen is the player's claim is true. He's actually making 80% of his shots, and the bad performance happened by chance. The other option, though, is that the player's claim is false. He is shooting something less than 80%. And so the sample result's not unlikely because the population value wasn't 0.8 in the first place. So if explanation one is plausible, then we don't have convincing evidence that he's exaggerating. His poor performance is just chance. It's going to happen. However, if it's unlikely for an 80% shooter to get a proportion of 0.64 or less, then we can rule out explanation one. So I don't know. We didn't have actual values as a class to look at. And eventually, next year, I'll be putting in a textbook image of what this looked like. But if I were to sketch it for you, they put in a dot plot where most of the values are centered at 0.8. So that's true, which should make sense. We know that the sampling distribution of sample proportions does center at the population proportion value. So it looks this-ish. And then they put a line where 0.64 is because that's what actually happened to our player. And then they point out that this did not happen very much. 3 of these 400 sets were 64% made or below. So this is showing that it's really unlikely. 3 out of 400 is a very unlikely success rate. Not even success rate, but it's just very unlikely for this to happen if he's truly an 80% free thrower. So yes, it could happen by chance. It is very unlikely that it happens by chance. So this gives us convincing evidence that the player is less than an 80% shooter. So this gives us convincing evidence. We've gone through this process before of using simulation to kind of support whether or not we think one claim is true or not. So it's similar to that, but we're going to get a process so that you can just look at the sample data and not have to simulate doing that multiple times. Okay, so what we just said The player claims that the true proportion value is 0.8. This is the claim that we're seeking evidence against. We don't think it's true, and since it's the one that we're starting with, that we're trying to see if we can prove false, it's called the null hypothesis. There will be two hypotheses. The null hypothesis is the first one. It will be abbreviated a lot by H sub 0 or H naught. Usually the null hypothesis is a statement of there's no difference. So for the free throw shooter, there's no difference from what he claims. Why do I have the word gives there? Oh, no difference from what he claims tells us that we would have our H naught be that P actually is what he claims. There's no difference from what he says and what's true. The claim that we hope, or possibly just suspect, to be true instead of the null hypothesis is called the alternative hypothesis. This is also abbreviated because that's a lot of words, and it's H sub A. In this case, we suspect that the player might be exaggerating. So our alternative hypothesis would be that we think the true population proportion is less than 0.80. The claim that we're weighing evidence against in the significance test is the null hypothesis. That we weigh evidence against. The claim that we're trying to find evidence for is the alternative hypothesis. Man, I can't spell evidence for. So, the alternative hypothesis is called one-sided if it's stating that the parameter is greater than the null value, or if it said that it's less than the null value. So after you've written it out, if this symbol is less than or greater than, then we call it a one-sided test. We will call it a two-sided test if it states that the parameter is different from the null value. So it could be either greater than or less than. So if we're looking at just kind of visual, if we just have that some parameter is equal to the null value, that'll be what we put for always in our null hypothesis. We'll always put equality there. However, in our alternative hypothesis, if you have that the parameter is less than the null value, this parameter could be the population proportion, this could be a population mean, but if it says it's less than the null value, or if it says it's greater than the null value, that's when it's a one-sided hypothesis. However, if your alternative hypothesis says that population, that's not spelled right, parameter is either greater or less than, which means just not the same as whatever null value, whatever number was started out. If it has not equal to, then it'll be considered a two-sided hypothesis test. That's going to matter when we really get into doing these tests for how we calculate a value later. But so for now, sometimes it's called a one-sided alternative hypothesis or just a one-sided test, or you could say a one-tailed test. I'm pretty sure I often say one-tailed test. So an example of what this could look like is that at a Hawaiian pineapple company, managers are interested in the size of pineapples grown in the company's fields. Last year, the average weight of pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wondered if this change will affect the mean weight of pineapples grown in the field this year. State the appropriate hypotheses for performing a significance test, and of course, we have to define the parameter of interest, which you're lucky that you're probably not writing this down because this is the part we all get annoyed at. So, I will be stating my null hypothesis and my alternative hypothesis. So I need to look at what parameter they're talking about. Pretty much always it's either going to be P or it's going to be mu. And if I read this one, it's talking about the mean. So I'm talking about what I think the population mean value is, mu. So the null always states equality. So we're trying to see if we have evidence against what they're stating. And what they're stating is that mu is 31 ounces. Now we're trying to see if we have evidence for it affecting it, which means maybe this irrigation system makes it less than, maybe it makes it greater than. We just want to know, does it make it different than the original 31 ounces? So we state our hypotheses and then always define your variables in the context of the problem that's actually stated. So this is the population mean. This is our true mean, our true average. And these are weights in ounces of all pineapples grown in the field this year. Example 2 is just another one going through, why is that broken up? Sorry. Usually I've read through these recently before I actually made you do this. Sorry. So as part of its marketing campaign for the Census Bureau advertised 10 questions, 10 minutes, that's all it takes. On the census form itself, we read this U.S. Census Bureau estimates that for the average household, this form will take about 10 minutes to complete, including the time for reviewing the instructions and answers. We suspect that the average time may be longer than what is advertised. So it's the same thing, although my directions are strange. So I'm still going to write it up as my hypotheses. I'm going to make sure I define whatever parameter variables that I'm using here. So if I can find the right thing that I'm looking for, sorry. Yep, lots of dead air, sorry. So again, we start first is your null hypothesis, then is your alternative hypothesis. I need to know what parameter we're looking at. I happen to give you 2 problems that's talking about averages. This can be another one with mu. We always start with it just being equality. Some people think that it's 10. We think, though, not that it's just not 10. We think it's longer than what's being advertised. So we're thinking it's something greater than 10. So I have this. I want to note that this would be a one-sided test because this has just greater than, whereas the one before it has not equal to. We said that whenever you have not equal to in your alternative, it's a 2-sided test. Again, it doesn't really matter right now, but it for sure will later. And then I need to tell what I mean when I say mu. So this is always the true mean, the population mean. I almost said proportion like a lot of you guys do. It's definitely not about a proportion. This is a true mean, and it's standing for the average amount of time that it takes to compute the census form. So once you have these, eventually we'll get to a process finding p-values. So we think of, a lot of times this gets related to like juries and courts and the law, because the null hypothesis can be thought of as like, you assume it's true unless you can prove otherwise. So somebody who's brought into court is assumed innocent unless they can be proven guilty. So the null hypothesis is the innocent part of this. The prosecution must offer convincing evidence against this hypothesis in favor of the other one. So guilt in that case. So if you're trying to convince them that they're guilty of stealing or something. In statistics, we deal with evidence provided by data. We're going to use a probability to say how strong this evidence is. So in our free throw shooter, we already said that p hat was 0.64. And it's evidence that, this is evidence against the null hypothesis that p is 0.8 and in favor of the alternative that it's less than. But is it considered convincing? Is it dramatically enough? So we looked at it with, well, I briefly described what it would be if we actually simulated this. But I want to actually know how likely it is to happen if he's really an 80% shooter. That's called the p-value of a test. So the p-value of the test is the probability of getting evidence for the alternative hypothesis as strong or stronger than what we observed if your null hypothesis is actually true. So it's called a p-value because it's a probability value. So assuming the null is true, well, how likely is it that what happens, or something more extreme than what we saw, could happen? So again, we use simulation. This is that super unlikely decimal I told you that we would have gotten. So it seems really unlikely. There's about 0.0075 probability of getting a sample proportion of 0.64 or less just by chance in a set of 50 shots. So what am I wanting here? Small p-values, that makes sense. We already talked about if it's unlikely, if it's less than 5%. If it's a small p-value, that's convincing evidence for your alternative hypothesis, because you're saying the observed result excuse me, is unlikely to occur if your null is true. Large p-values, however, fail to give convincing evidence. It doesn't necessarily... Sorry, I can't write and talk at the same time. It doesn't necessarily say that for sure he's innocent. It's just we didn't have enough evidence that convinces me otherwise. You're innocent until you can be proven guilty. It's true unless you prove otherwise. Otherwise, you just go back to assuming, well, it's probably true. So, what we're looking at on this next one, calcium, vital nutrient for healthy bones and teeth. The NIH recommends a calcium intake of 1,300 milligrams per day for teenagers. They're concerned that they're not getting enough calcium on average. So to see, this is what their test is. So the null hypothesis, we're going to assume for now that it's actually 1,300 milligrams. So we're assuming that that's what they get. They're going to test to see if it's some amount less than that. So we're going to see if we have enough evidence to say that that's actually the true one, that we can get rid of the null. And mu is defined as the true mean. So they ask a random sample of 20 teens to record what they eat. They compute the calcium intake. They find X bar and S sub X, so they get the sample mean and sample standard deviation. They perform a significance test. Here's what we're looking for. They get a p-value of 0.1404. I want to know what this would mean for the null hypothesis to be true in this setting. So what this means, if the null hypothesis of mu equals 1,300 is true, because we assume it's true unless we prove otherwise, this means that the mean daily calcium intake in the population of teenagers specifically is 1,300 milligrams. So it has nothing to do with the p-value. Just if we know the null hypothesis is true, this is what it means, that the average daily intake of calcium for the population of teenagers actually is 1,300. The p-value shows us that we are seeing a probability of 14% of this extreme or something more extreme in our sample. So what I'm going to do to interpret this, you always start out by assume the null is true, because that's how you start out every problem. Assuming that the mean daily calcium intake, because that's what our null hypothesis is talking about. So assume that in the teen population, it is 1,300. So assume that's true. Assuming that's true, then that's the probability of getting this type of sample mean. So there is a 0.1404 probability of getting this sample data that's this extreme or something more dramatic than this. Or something even more dramatic, so something smaller than that. just by chance, just by sampling variability. Assuming we're using a random sample of 20 kids. So this is the probability that I get that sample mean or something even smaller for this type of value. It's the strength of the evidence for our alternative hypothesis. So it's the strength of our evidence against the null hypothesis. In the preceding example, the sample mean gave some evidence that it was less than 1300 because that 1198 number is less than 1300. The p-value is the probability of getting evidence for h sub a as strong or stronger, which is when we said that low or smaller than the observed result, still assuming the null is true. The p-value then can be a conditional probability. It's another way that you can kind of think about this happening. So for this healthy bones example, we could say that the probability of getting a sample mean that is equal to 1198 or smaller, so less than or equal to 1198, given that the null hypothesis is true. So given that mu is 1300, that probability is the 0.1404. If, in a different example, we are looking at a population proportion being 0.5 versus the population proportion not being 0.5, so now I'm switching it to a two-tailed test. If it was based off a simple random sample with this sample proportion, we're seeing, hey, I'm getting a value that's not 0.5. So there's some evidence that my alternative seems to be the more likely result, but is it convincing? So in this case, evidence for h sub a as strong or stronger than the observed result includes any value of p hat greater than or equal to 0.65. So I'm looking for something even higher than 0.65, as well as any p hat value that is less than or equal to 0.35. Because if I'm talking about this value, 0.65 is 15% above that. 0.35 is 15% below that. So it's just as different than the null from the null hypothesis as 0.65 is. So it would be a two-tailed test because you have these two things, greater than or equal to 0.65, less than or equal to 0.35. So we get these two tails. In this scenario, the p-value is equal to the conditional probability of finding a sample proportion, so p hat, that is less than or equal to 0.35, or p hat value of greater than or equal to 0.65. Again, given the condition that your null is true. If you keep assuming that it's actually whatever was in the null, how likely is the result that you got? So there's some stuff still left about making conclusions and the errors that can be made, but this is going to take for freaking ever to upload. So I'm going to stop here and then do a second part of this lesson. I wouldn't try the practice that accompanies this. It's mostly just for sanity's sake when trying to upload this. So